Good afternoon, students. We will start the class within 5 minutes. So just wait for a few minutes. Okay, then I will start the class. We will do some numericals that is based on the torque equation or the induction machine. So all of you must take the copy and pen with the calculator so that it is easy to make the mathematical calculation. So I will join in 5 minutes. So wait for 5 minutes. Next 5 minutes. Okay. Thank you. So this is the normal. We were discussing about the torque speed characteristics of the induction machine. So this is the special curvature or your torque speed characteristics of an induction machine. Here we can see that the explanatory part or the graph representing how the torque speed curve is torque speed curve represents the induction machine, that is power and torque. So from here you can see this is the negative synchronous speed. From there we have started the graph, and up to this is the synchronous speed where the synchronous speed is 0. Then this is called braking or plugging up to from minus synchronous speed to 0. Okay, that means the synchronous speed it is gaining its value, and up to this point 0 value, this is called braking or plugging. Then after, as the synchronous speed increasing, enhancing from 0 to somewhat gaining its speed for your synchronous speed, then that condition is known as your motoring condition. Then that condition is known as your motoring condition. So following that, if we draw a graph, then it will represent somewhat like this. And at this point, at point 1, let us say this is the this is the area, this is the margin for y-axis. That we can say that this is the starting torque. The starting torque for your motor, induction motor, is quite higher, and the motoring is at the synchronous speed. The motoring speed torque will be reduced to 0, and as the synchronous speed again increasing, but the sleep, as the sleep is decreasing, the sleep value from varies from 1 to 0, then 0 to 1. For the negative sleep value, the when the induction machine operation works, then it is named as your induction generator, or you can say regenerative braking or regenerative braking. For that value, you can say that for regenerative braking, the variation of the sleep is from ns to 2ns, and the sleep varies from 0 to -1. 0 to -1, that represents the negative sleep, and the synchronous speed is of the higher value than the synchronous speed. That is for generating. So this is the curve that represents your motoring and regenerative braking, or generating or plugging or braking of the system induction machine for the car. Now there is a explanatory purpose for your three more. That is, first one is operating region. Now operating region, that the operating region for the induction motor is this one. That is when AC sleep is greater than 0 but less than greater than 1 but less than 0. That is the operation of the induction motor. And similar things occurs for your speed. That is, speed generate from value from 0 to ns. That value generate from 0 to ns, that will give the value of synchronous speed from the range from value, that is ns is greater than 0, but or rotor speed is greater than 0 but less than synchronous speed. That will give you the motoring operational, or you can say operating region. Okay, for three reasons. First one is your braking or plugging. And from braking plugging, the rotor speed is less than 0. The slip value is greater than 1. Now that in this case, for the first portion, the torque is positive while the speed is negative. As you can say, this is the speed is negative. Considering the power conversion equation, as we know, the power conversion is given as 1 minus s into power gap. As we have already know, the 1 minus slip into power gap is known as air gap power, is given by the conventional conversion power. No, this is the converted power, you can say conversion power. So it can be seen that it is written explained here that it can be seen that if the power converted is negative, can be seen that if the power converted is negative, that means if the conventional power becomes negative, then the air gap power is positive. Then the air gap power will be positive. Okay, for that value, the slip must have the value greater than less than 0. Okay, that means the value must have slip must have greater than the value of 1. That means if the value of slip greater than 1, then this whole system will become negative, and for the negative air gap power, this conventional power conversion power will become positive. So that is what written. The power is flowing from stator to rotor and also into the rotor from the mechanical system. This operation is called plugging. So this is the plugging operation. That is, sleep is greater than 1, then it is known as plugging, and if sleep is less than 1, as sleep is greater than 1, then it is known as plugging or braking. When sleep is less than 1, or less than 0, then it is named as your regenerative braking or generating thing. So for that purpose, it is named as your plugging. Now, this mode of operation can be used to quickly stop a machine. Regenerative, or you can say braking or plugging. Braking is mainly applied to stop a machine. So that is from that concept, we can say that this mode of operation can be applied to quickly stop a machine. If a motor is traveling forwards by interchanging the connections to two of the three phases. That is, switching two phases has the result of changing the direction of motion of the stator magnetic field and effectively putting the machine into braking mode in the opposite direction. So this is the part of the braking. This is the region of the braking. So the next is your motoring. Motoring range from sleep range from 1 to 0 and the synchronous speed range from 0 to ns. So these are the range through which we can say the operation mode is active for induction motor. The motoring is for 0 to ns, that is rotor speed lies between 0 value to synchronous speed and sleep lies from 0 to 1. Okay. Torque and motion of the induction machine will be same in this motoring mode, and this is the most common mode of operation for the induction motor. Okay, this is the normal that we have discussed in the motoring condition. Torque and speed must be derived from the DC concept. So this is the main. Just you have to remember the range of the motoring mode. Just you have to remember the range of this motoring model. What is the range of synchronous speed? What is the range of slip for motoring? Now, third operation is your generating mode. Generating mode, you can say rotor speed is greater than synchronous speed, but the slip is less than 0, or the slip is negative. Slip is negative and the rotor speed is greater than synchronous speed. So in this mode, again, torque is positive while speed is negative. Here you can say torque is positive, but torque is negative. Sorry, torque is negative, but the speed is positive. Here you can say that torque is positive and while speed is negative. It is written wrong because according to the graph, you can see torque is this is the y-axis and torque is decreasing and the speed is increasing. That means speed is already in positive, but the torque is decreasing. Okay, accordingly, the like the plugging portion, the conventional power is represented again by this formula: 1 minus slip into air gap power. Now, indicate if the power converted is negative, that means if the power conversion is negative, in that case, the air gap power must be positive. So the air gap power must be positive. And for the air gap power, if the positive, the slip is less than 0. Less than 0 means it will be less than value of 1. And that value, if the value of less than 1, the whole process or 1 minus s power gap into power gap will become positive. And in that case, the power conversion is will become negative. In this case, the power flows from the mechanical in the generating condition. Power flows from the mechanical system to the rotor circuit, then across the air gap to the stator circuit and the external electrical. That means in generation port, in induction motor will work as an induction generator. That means if the electricity will flow outward from your induction from the rotor part to the stator part. That is the case of that. That is the for your the named is a regenerative braking. That is the concept of your regenerative. That is the name that given as regenerative braking. Okay. Now, the motoring torque characteristics is defined by this equation. First, we should know the basic terminology that is related with your torque of the induction machine. So here you can say that this is starting torque, then pull-up torque, then breakdown torque, then normal operation. So first, let us say the motoring region of the induction machine torque speed curve is the region of the gated interest. So it is given as this is the starting torque, this is the starting torque, this is the slip where s equal to 1. This is the slip where the value becomes 0. This is the synchronous speed having the value 0, but the synchronous speed is become at synchronous speed. So this is the slip is increasing from the left hand direction, but the speed is increasing in the right hand direction. That means slip and synchronous speed or rotor speed is inversely proportional to each other. Now, from the starting point, if we increase the value of the synchronous speed, then the high slip region is there. But after a pull-out torque is provided, pull-out torque means the machine will run out of the synchronism. That means in that case, the delta will become 0, or the load angle that comes in the electrical machine, that will become 0 value. Okay, that will become that will become 90 degree value. and in that case the slip will have the value lesser. Low value of slip will be there. That means in that case, synchronous speed is approximately equal to the full load speed. Okay, that is the condition. So this is called lower region of the slip. This is the lower region of the slip. That is, this will have the very much less amount of slip will be there. Let us say 0.003 will be there, or 3% slip. The 3% slip will be there. Then there is a full load torque is provided. Then there is a no load torque is given in this case. So accordingly, you can see that for small values of the slip, the graph the explanation of the graph is given here. For small values of the slip, the torque is directly proportional to the slip. So you can say for a smaller value of the, as we have discussed in the previous slip, that is the smaller value of the slip, the torque is directly proportional to the slip, and for a higher value of the slip, the torque is inversely proportional to the slip. Torque is inversely proportional to the slip. For higher value of the slip, the torque is inversely proportional to the slip, but for smaller value of the slip, the torque is directly proportional to the slip. Okay, so you must draw this diagram so that you can understand the basic concept regarding a motoring region characteristics of the induction machine. Okay, now let us discuss about some terminology that is given here. First one is starting torque. Second one is a pull out torque. Pull up torque. Third one is a breakdown torque. Fourth one is a normal operation. Fourth one is your normal operation. Now here you can see that torque at in a starting torque at zero speed, torque is at zero speed. Then for starting torque, this starting torque is 1.5 times the full load torque. Okay, that is the high starting. If you need a starting torque of higher value, then the induction motor is very much applicable in those places. Second one is pull up torque. Pull up torque is the minimum torque developed by the motor while accelerating from zero speed. Pull up torque is the minimum torque developed by motor while accelerating from zero speed. Okay, that means when the motor starts from its zero speed, then the torque that produces the minimum torque that is produced in the induction motor is known as your pull up torque, and that pull up torque is greater than full load torque. That pull up torque is greater than the full load torque, but it is less than the starting torque. Is the full load pull up torque? Wait a minute. Now this pull up torque is greater than the full load torque, but it is less than the starting torque. It is less than the starting torque. So these are 2 points regarding a pull up torque. Next one is a breakdown torque. Next one is a breakdown torque. What is breakdown torque? The torque that is the maximum torque that the motor can develop is called breakdown. After this torque, the motor will break down its strength, and it will not operate properly. That is named as a breakdown. The maximum torque that can develop in a motor is known as breakdown torque. That is operationally 2.5 times that of the full load torque. Breakdown torque is 2.5 times than that of the full load torque. Okay. Now next point is normal operation. Normal operation is given at full load. The motor runs at n rpm. Let us say n rpm, or you can say 3000 rpm. Whatever is the value you want to take, you can take it. So normal operation operates at full load when the motor operates at n rpm. Now the rotor speed decreases. The important point for normal excited operation is given at first. It is the full load. The motor runs at n rpm. Second one is rotor speed decreases slightly. Rotor speed decreases slightly from synchronous speed with increasing load torque. Rotor speed decreases slightly from synchronous speed with increasing load torque. Then third point is motor will stall when the load torque exceeds the breakdown torque. Okay, so these are the three important points regarding your normal operation. Then there is a torque speed curve normal mode for the motoring mode, or you can say for the induction motor. The torque speed curve is given by this curvature. You can say the torque is in the y-axis, the rotational speed is given in the x-axis. So here you can say this is the log rotor torque. Then there is a pull-up torque, the minimum torque required for before the starting. Okay. Then there is a breakdown torque. That means beyond this torque, it will not exceeds from its value. This is the maximum torque that a motor can withhold. and as the speed increases, this torque will break down, and this will decrease with the increment the speed. This is the full load torque. This full load torque is given as the nominal torque also. This is the full load torque is given by T, and at the synchronous speed, at the full load synchronous speed, the torque will become zero because the machine will is an unoperational condition. Regarding an unoperational condition, the full load torque, this is the rotor speed. So the total torque equation of the induction machine is given by this equation. That is 3I2 per R2 upon S omega S. This is the speed of the induction machine. So accordingly, if we draw a circuit diagram, this will be the circuit diagram of the induction machine of the system. Okay. Then that if we apply the Thevenin equivalent, if we apply the Thevenin value of this circuit, then we can apply and use the same concept by using. Okay. So this is not the explanatory part for you. The starting torque, you must remember that this one is the starting torque of your induction machine, that is related with your directly 3 Vt v square th r2 divided by synchronous speed rth plus r2 square plus xth plus x2 the whole square. So this is the starting torque of the induction machine. Then there is a torque produced at a slip by induction machine. This is the ratio, that is starting torque divided by maximum torque equal to 2 divided with slip at maximum slip plus maximum slip divided by slip. So SM is the slip for maximum torque and TM is the maximum torque. So these are the some examples that we have discussed. Now, what is the effect of rotor resistance that we should consider? Now, let us take an example. Let us take an example regarding this before going to the starting of an induction motor. So here you can see that here it is given. Wait for 2 minutes, then I will show you some. I will solve this numerical. Wait for 2 minutes. So we will be discussing about the torque speed characteristic. So let us discuss some of the numerical based on the those concept. So here you can see that a question is given: a 460 volt, 25 horsepower, 60 hertz, 4-pole star connector wound rotor induction motor has the following impedances in ohms per phase referred to the stator circuit. That is R1 is given, R1 and X1 is given, then R2 and X2 is given, then XM is also given. Then it is asked that what is the maximum torque of this motor, then at what speed and slip does it occur, what is the starting torque of this motor when the rotor resistance is doubled, what is the speed of at which the maximum torque now occurs, what is the new starting torque of the motor. So basically, we have to use the basic formula that is related with the induction machines. So by using the above concept, we have the following formulas. That is the Thevenin voltage of this motor is given by the method for finding the value of maximum torque. As we have discussed the maximum torque formula, you can see here the maximum torque formula. So maximum torque formula is this one. Okay, that means we have to calculate first. We have to calculate the VTH using this circuit diagram. This is the VTH, supply voltage. This is the Thevenin resistance. This is the Thevenin reactance. This is the rotor side reactance. This is the rotor side resistance, including with your slip, and the current flowing through the arc. So first we have to find the value of VTH. Accordingly, if you put the value of VTH, we will find the value of the starting pitch. So for finding the value of VTH, we have to calculate this. You have to use this concept, this formula, that is V5, that is XM, that is supply voltage, then XM magnetizing reactance, then R1 stator resistance, then XM total reactance of the machine, X1 plus XM ka whole square. So from here you can see that XM has the value. XM has, if you solve this is star connection. Star connection we have the line voltage equal to root 3 into phase voltage. From there, if you calculate the value of 460 volt in phase voltage, that means you have to divide 460 volt divided by your root 3. From there, you will get the approximately 266 volt. And XM have the value 26.3 ohm. Just put the value of XM. Then there is a R1 have the value 0.641. Put the value of R1. Then X1 and XM is also there. That is 1.106 ohm. And XM is 26.3. From there, by putting the value and by proper doing the mathematical calculation, you can see that the value will have the 255.2 volt. 255.2 volt is given. Now accordingly, if we want to find the value of resistance of the Thevenin resistance in the induction machine, you will get R1 approximately equal to R1 within the bracket XM divided by X1 plus XM ka whole square. That is the formula regarding your Thevenin resistance in induction machine. So by putting the proper value, you will get the rotor resistance as 0.590 ohm. Now the Thevenin reactance is approximately equal to X1. So this X1 is approximately equal to 1.106. Now we have the total parameters that is required for maximum slip, that is required for slip, that the R2, we have the value of R2. We have the value of RTH also. We have found the value of RTH at 0.590. And XTH we have introduced 1.106 ohm. Then there is X2 value. Then X2 have the value 0.464. 0.464. Now by putting this value, you will get as maximum the slip at which the maximum torque occurs is given by this value 0.198, or you can see in percentage form. You will get that 19.8% of slip will be there for your maximum torque. Now, for that value, if you want to find the value of corresponding mechanical speed, you have the value mechanical speed equal to 1 minus h into synchronous speed. So you have the value of slip as 0.198. So 1 minus, it is less than value of slip is less than value of 1. So it will positive. So it will 1 minus 0.198. Synchronous speed is 1800 R upon per minute. 1800 R upon per minute. That is given. So from there you will get 1444 R divided by per minute. That is the mechanical speed of the induction machine. From there, if you want to find the maximum value of the torque, just put the value, you will get all the maximum torque as 229 Newton meter. Okay, so this is the maximum torque that is going to withheld in this numerical, that is 229 Newton meter. Now, if you want to find the value of the starting torque, if you want to find the value of the starting torque of the motor, you will get this. You have to just put the value of slip as 1 in equation 1. So this is the equation 1. You can see that. So this was the torque equation. This is the maximum torque. When you put the value of S equal to 1, you will get this equation. That is, when you put the value of the starting torque equal to S equal to 1, you will get this equation. Starting torque will become 3 VTH square R2 divided by synchronous speed within the bracket RTH plus R2 ka whole square plus XTH plus X2 ka whole square. We have the value of VTH R2 synchronous speed RTH R2 XTH X2. Just putting the value, you will get the starting torque. As you can see, the maximum torque was 229 Newton meter, but here the starting torque of this motor will become 104 Newton meter. 104 Newton meter is the starting torque of this machine. So this is the second part. The third part we have to calculate is when the rotor resistance is double. That means R2 become 2R2. What is the speed at which the maximum torque now occurs? So for that, just in the case when rotor resistance becomes double, the slip at maximum torque doubles too. Okay, because if we decrease, if we value the in the circuit diagram, we have the value of, let us say, if we increase the value of rotor slip by double, then the whole process will be double. So in the similar manner, it is written here, if the rotor resistance is double, then the slip at maximum torque doubles too. Therefore, slip, as we have the value of slip as 0.198, so multiply with 2, you will get the maximum slip as 0.396. You have the value of 0.396. So at the speed, so the speed at the maximum torque is given by the mechanical speed equal to 1 minus s into synchronous speed. We have the changed value of slip as 0.396 or 39.6%. Just put the value, you will get 1087 r per rotation per minute. That is RPM. That is rotation per minute, or you can say RPM. So the maximum torque is still, but the maximum torque is still 229 Newton meter. So that now the starting torque will varies. Now putting the value of a starting torque formulas parameter, you will get the 120 Newton meter. So accordingly, here the starting torque was 104 meter. Here starting torque becomes 170 Newton meter. That means it is increased by 66 Newton meter by increment in the slip. By increment in the rotor resistance, the starting torque is also increased. So this is the numerical based on the your torque speed characteristics of the induction machine. There is another method. This is all about the torque speed characteristics of the induction machine. So then we have the different types of starting of the induction motor. So you can see here there is a explanation of the how induction motor starts is given here. Okay. So we will attend the next session. That will be of 20 minutes. So I'm going to in this session. Kindly rejoin within 5 minutes in the next session.